something going on. So I just want to jump in for the
You worry about rotor on those side thermal stuff?
Oh, for sure. But so you have to judge the strength of the wind. For sure, if it's stronger, then okay. If you judge it, it's a mental thing. If it's a strong, if you're in a strong thermal, and let's say you go into a lee side, you're in a strong thermal, and you have a really strong wind. Now you got to make a decision. Is that thermal stronger than the wind? If it's not, sure, then you're going to turbulate. But if you think it's stronger than the wind, you go for it. And the typical example of that is at Diablo many times, because you go up in Diablo and you're getting a really nice strong thermal, but on the lee side of it, you'll have some winds ripping through there. So you have to make the decision, is it going to be strong enough to go over that valley? Because if you sink, you're going to be in big trouble, or not leave. So
that's a great question. My rule tends to be about a 1-to-1 glide. Like, usually you want to keep a very steep glide for getting back. You want to make sure the wind that if you're deciding the thermal behind, like up and behind a ridge line, first always make sure that wind isn't stronger than your forward speed. If it is, it's very advanced flying. When you're starting to go over ridges where you know the wind is stronger than your forward speed, that's very advanced cross-country flying, and that's still, you'd want to have caught that thermal not at the ridge line, well out in front, so you're like maybe 1,000 feet over and or above the ridge before you're going over. But usually, exactly, you want to evaluate that thermal. You never want to take a weak thermal over the back. If you're taking a thermal over the back, you want to make sure that, I would say, you have, if you lose it all of a sudden, then you've got the penetration speed to go forward, and you haven't put yourself like 2-to-1, 3-to-1, 4-to-1 glide behind that ridge top, because then you might not make it back in front of the ridge, and you might be forced to run, or just depending on how the lee looks, it can put you in a whole predicament.
Just a quick show. In back of Diablo, if you take a weak thermal over and you're going to sink, you have big power lines right in back here. So you got to be real careful about that.
Shock some sense into it. Okay. Yeah, so speaking of small thermals, sometimes you're connecting, you got to be a little careful when you decide to circle, because certain thermals can feel really good when you enter them, but then by the time you've done a full circle, you're lower than you started, and you've lost. And sometimes gusts can feel a lot like entering a wind gust can feel very much like you've entered a thermal. And I like to call them sucker thermals. Martin always would remind me, like, "Oh, Dad, you just circled in a sucker thermal." Or he would tell me, don't circle, it's a sucker thermal. So there are little sucker thermals that kind of, my sort of general rule of thumb is, if you can get lift for about 3 seconds, you should be able to fit a circle into it and go up. But it can be, there are certain things that can feel like, wow, this is great, I'm going to hook this thermal, and by the time you've brought your full circle around, you're lower than where you started. And if that happens way up there and you got a lot of room, that's fine. If it's down low, then you're that much closer to sinking out. So just kind of figure out, depending on how, a lot of this is also personal, what kind of turn rate you feel comfortable with. And if usually when you start flying, you're not hooking really tight, and you should be also careful about that, because you might not know the spin point of your glider and all these things. So you want to, kind of figure out how sometimes time your circle in a thermal, I would say. And I was always surprised. I did that a few times. I was like, I'm about 12 seconds. I always thought it was far less than that. But 12 seconds, so, that means if you probably want to be almost 4 seconds going through lift to get a 12-second circle in there. Kind of that whole, diameter times pi.
You got to jump in again. We all talk about circles, but no one really thinks about ovals. The wind's pushing the thermal. If you do a circle, you half your wing and then you're out of it. You think about just spending a little more time going downwind, doing a oval type of shape instead of a regular circle. That's my 2 cents.
Yeah, and I found that's true. The oval works. It works different ways. Sometimes you actually the thermal's kind of tracking up the hillside. You got to follow it back towards the hill. But sometimes in stronger winds, you almost have to like spend a little more time on the upwind side of it, just to not fall out the back. So it's not always in wind do you track it. Do you spend more time on? You're either tracking it slightly upwind or sometimes you're tracking it slightly downwind, and that's just the art of thermaling. Just kind of, I mean, to this day, 25 plus years later, I'm still trying to figure out thermaling. I mean, it's you spend a lifetime trying to figure it out. Yeah. Yeah. Okay, so let me see the weather stuff. Okay, yeah. Why? Surface heterogeneity. So different types of surface. You know. Part of the reason why, 2 things will make the air more buoyant. You either heat it and make it less dense, or you introduce a gas that's less dense into it. Now, water vapor is less dense. So, yes, adding water vapor, evaporating water vapor into the air makes it less dense and therefore more buoyant. But at one time, just out of curiosity, did the math on this, and it's about 12 times more energetically expensive to evaporate water into the air to decrease its density than to just heat it. So that's why desert areas where there's no water under strong sun produce really cranking thermals, especially over dark surfaces. Whereas the more humid or wet the surface is, like grassy areas, tend to produce mellower thermals because a lot of the energy that's coming in is being used to evaporate water. And yes, evaporating water will make the air less dense, but at a much higher price. So for the given amount of energy, you're just not going to produce as strong a thermal. Go ahead. Okay, so cloud suck is when you arrive at the base of clouds. The clouds, before there's a significant inversion, it could be a lot higher. So the clouds can be fairly deep. Small fair weather cumulus clouds that are not very deep usually won't have much cloud suck because that inversion is strong enough. Even despite the fact that you're now forming cloud, you change the rate of cooling because now you're releasing condensation of water releases heat. So it's almost like you've boosted that thermal. But if they're really kind of fair weather cumulus clouds, they're not going to have the cloud suck. The cloud suck's going to be the bigger clouds that have maybe 1,000 feet or more, I would say, of vertical development. They might then there's a boost. Then that thermal arriving there gets a little bit of an acceleration. So if you kind of thought of a speed profile, it would take a little while for it to ramp up and it would have a pretty high speed in the middle. Normally, as you get towards the top, that entrainment zone, things are slowing down. But that cloud, if it's tall enough, will actually force an acceleration that it's accelerating as it enters that cloud, so therefore underneath that cloud there'll be a little bit of an acceleration to the thermal. So that, I would kind of rule of thumb is how big is that cloud? Is it towering? Sometimes they say taller than wide is a little bit of an indicator, but you can get some really wide and tall ones, like when you get out over Nevada, and those you just have to be careful. Yeah, they're just tall and wide, and they're big. Now, the other thing to watch out for in general with clouds is the transition from shallow convection to deep convection. So shallow convection is boundary layer convection, basically from the ground to the top. If there's blue thermals, that would just be the top of the lift. If there's fair weather cumulus, it'd be kind of for us cloud base or the tops of those cumulus. And then deep convection is basically cumulonimbus thunderstorms. It's the whole troposphere now convecting. So like I said, the boiling of air, we like to fly in the air that boils just from the ground up to kind of fair weather cumulus top. several thousand, or sometimes in the high mountain deserts, 10,000 feet deep, but still not topped with large towering cumulonimbus clouds. And that transition can be very quick. You can, it can be a thunderstorm once it does decide to grow somewhere. If there's a lot of humid air that's accumulated, and part of how you allow a lot of humid air to accumulate is you've got a pretty strong inversion. If there wasn't a strong inversion, if right from the morning there's really tall, it'll start out as tall, skinny cumulus clouds, but kind of a day that's going to storm kind of gives you the hints in the morning hours if it's going to storm early. Now, some days are just capped by a strong inversion, and it'll be the one afternoon thunderstorm over the high ground that'll break through. But when it does, that can happen, fairly quick. That can be, usually there's kind of the 15 to 20 minute convective overturning cycle. So like a thermal will often from the ground to its very top be about 15 to 20 minutes. But so will air in a thunderstorm, which means it's got to go from the surface up to 30,000 feet in about 15 to 20 minutes. So you can think of the ascent rates in that. And in thunderstorms, we can become confetti to a vacuum cleaner is the way I like to think about it. I mean, short of free falling out, we're going up, and there's that great story of Eva. Luckily she survived, but she got hoovered up to 30,000+ feet and spit out and survived to tell about it. But most people who've been through that haven't survived, like getting into a thunderstorm.
What about the benign usable of clouds? Like if you're approaching, say, a cloud street, do you find it usable material like right under the cloud street?
Yeah, part of that is because, a lot depends right on how deep the clouds are, but you're still, the nice thing is if you split into thirds, the bottom third, the thermal's still accelerating. It's got its best speed in the middle third, very crudely, and then the top third, it can be slowing down. But if still kind of the top third is the cloud, let's say, or you could find more or less, you can zoom along, because you're still somewhere near the top part of the second third or the bottom part of the last third, which would be a really nice lift. And the clouds are marking it too, so you can just kind of zip along on a cloud street. Speaking of that, kind of goes to the convective patterns that like to set up the most. There's two, if you have the same kind of surface, like an open body of ocean, so it's all the same surface, same warmth. If there's wind, you'll tend to set up cloud streets. If it's not windy, you'll tend to set up this honeycomb or cracked mud looking pattern. And that'll, as soon as you start to introduce different surface types, that'll break down. As soon as you throw in, dry versus wet ground, mountain types, that starts to that starts to break down a little bit. Okay, let's see. In the mountains, okay, so I want to say just why mountains are often just better for thermals. Couple things. You get often, especially the mountaintops, tend to be drier unless they're snow covered. Tend to be a little less vegetated, so you got a lot more rocks. When you create a lot of deep valleys, you get kind of what they call the valley amplification factor. You basically, a smaller volume of air is being heated by more surface, so the heating rate for that amount of air can be greater. Also, if you go up to altitude, another thing to think about is the air is less dense, so with the same heating, there's, in a particular amount of particular volume, there's less air there. It's less dense, so it takes less energy to keep that cubic meter, let's say, of air. So it's easier for the thermals to kick on. And one other thing, often in the mountains, the air tends to be cleaner. So if you see a really clear air day and the sun just feels hot on your face from the morning, things might turn on a little quicker because clarity of the air makes a big difference. If you don't have, if you've got a lot of aerosols, especially in the morning hours, the sun's got it's being attenuated. The other thing about a lot of aerosols or fine dust particles in the air is that in itself is acting not quite like an inversion, but it's in a stabilizing fashion, because all those fine dust particles are intercepting the sun's rays, and they can heat. Normally, like clear air lets the sun pass through pretty much straight through and start heating the ground directly.